Okay, so you guys may start the workshop now.
Okay, so hello everyone. My name is Rishavar, and I will be introducing you to this linear regression. So basically, this workshop is divided into four subtopics. First will be this linear regression, then this logistic regression, and third one will be this regression stuff, and finally the implementation of linear and logistic regression using this Python libraries and Pytorch. And if there's time left, then Cassandra coordinators are going to discuss their assignment that they have given to you guys. Okay. So let us begin with this linear regression first. So linear regression is nothing but the usage of linear models for making predictions using some linear function of input features, right? So let us understand how we are going to make linear models using some example data set. We are given a simple data set for house prices. Every data point here is of format X and Y, okay? So where X is your house price and X is your size, that is the feature which is in feature square, and Y is your target variable that is in price, right? So since this is a data set with only one variable, that is size, so we can say that the equation of the line, that is Y is equal to mx plus c, can fit over this
Rishabh,
data.
one sec.
So here we have,
Yes, your slides are not visible.
wait a minute.
Like his slides are not changing also.
So this house price slide is visible now, right?
Yeah, now it's
Okay, what I was saying that a line that is y is equal to mx plus c can clearly fit over this data set because we are having only one variable, right? So we'll be giving x and y in training data set. So what we need to do is to learn these m and c parameters, that is slope and intercept parameter, according to the data, so that we can predict house price or some new size of the house, right? And yes, this problem belongs to the supervised learning, as we are having output values to train our model, and also regression because we are going to have some real valued output. So this is the data set in form of a symbol. There are some terminologies associated here. This is M. M, it is nothing but the number of the training examples in our training data set. And X is your input variable, and Y is your target variable, right? So it is a pretty simple data set, no big deal here. So we have this training data set ready, right? And the size of the house also. So what we need is to have some function which will map our X to Y with using some learning algorithm, and that some function is nothing but your hypothesis, right? So in short form, we are denoting it with this H. So the real question is that, like, how we are going to represent it. So as I told you earlier, this data set is only having one feature, X. So some line with some values of the slope and intercept can fit over this data. So, and also we need to find some good parameters like perfect values of the slope and intercept parameter so that our line can fit over this data. So let's have some idea about it. So yes, this training data set we have ready, and this is the hypothesis we have. This linear equation of a line, where this theta naught is your intercept and theta 1 is your slope. So we need to find these parameters, theta naught and theta 1. So let's say this is some data set that you have been given, and now you need to fit a line over this data. Well, a good line can be this green one with some slope and intercept. And when you will input your x value in this hypothesis x, then you will get your prediction as y predict, right? So let's say you have another line, this blue one. So now the question is like how we are going to compare this blue line and this red line, like which one is having a good fit than other. So right, we need some mathematical term that can distinguish us between the good fit and the worst fit. So anyone from the first year do have any idea what that mathematical term can be?
So a good fit can be defined as the line having equal distribution of points on either side, maybe.
But you need some mathematical form, right? Uh, that was a good approach. Like the perfect answer can be like this. You can calculate what the error we are getting from any kind of a line, right? So let's say this is the point we have x, and this is much is the error we are getting. That is simply nothing but this y spread minus y. Okay. Similarly, for the other data points, this much error you will be getting, right? And for this blue line, this yellow errors are here. Okay. So you can clearly see the error is less for these green lines, right? And for as compared to this blue one. So thus we can say that this green line is a good fit, right? So that mathematical term is nothing but the your error. We need to like square it, or squaring must be done because it will give us the true estimate of our error. And we need to sum over all the examples. And if you don't perform squaring, then this term can be error term can be positive for some examples and also negative for some examples. And when you will going to add over that, your ultimately error become less because the some terms are positive and some terms are negative, which is like false. So you need to perform squaring over the error of the each data point and then sum over. So this is the cost function we reached here. The cost function or loss function or error function, there are multiple names of it. So you just need to square the errors that you're getting for all of the examples. And then you need to average it by dividing with this 1 by 2m, right? So this is the cost function. So anyone is having a doubt in this cost function?
Why 2m?
Just for averaging. You can divide it by 1 by m, but for making calculations easy, we are going to divide by 2m. It will be in gradient descent part, why I take 1 by 2m. Right? I
Okay.
will tell you later. Okay, so let's understand what this cost function worked. So we have this hypothesis in form of a linear equation, this simple line, okay, with these parameters theta naught and theta 1. And we have formulated the cost function here, some squared error actually, averaged over all of the examples, right? And what we need to do is to choose theta naught and theta 1 in such a way so that we can get our loss function as minimum as possible, okay? So for understanding it, let's take a simplified version of this hypothesis. Let us assume this theta naught is 0. Okay. So you will get this equation. It is nothing but the equation of the line passing through the origin, where your theta naught is 0, and your hypothesis equation is only dependent upon your theta 1 parameter, right? And thus this your cost function is evaluated here, which is also dependent upon only theta 1 parameter, and you need to minimize it using this theta 1 parameter. Okay. This is the data you have been given, right? And you need to find what perfect line can fit over this data, right? So this is the hypothesis that we have. So I guess from first year, can anybody guess what this theta 1 value should be? That
1.
line which can, yes, perfectly. We have one y is equal to x is the line that can fit over this data perfectly, right? And when you're going to calculate the error function, that you have made because of this line, then you'll get this 0 value, right? Because this line is completely overlapping with these other data points, right? So this, I guess, error function is ready. This clear to you guys? And this is the like minimum cost you can get. 0 is the minimum cost because we are squaring the errors of the individual data points, right? So So this is the minimum cost you can get, but not in just one guess you are going to have this error function value minimum. So multiple guesses will be made, and these guesses are not like based on some random strategy. They are based on some strategy, and our ultimate strategy is to minimize this cost function. Okay. Now what we want to do is to learn the like how this theta1 is related to this cost function. Okay, so I will be plotting a graph in simple words with some values of the theta1. I will be checking what my cost function is having value, right? Just to read the relation about this j theta and theta. So this is the previous slide I have shown you. Here we have choose this theta1 value as 1 such so that we get error as 0. Now if you have this error as like theta1 value is 0.5, so here you will be having some error, right? When you will be calculating this error using this formula, then you have this error value as 0.58. Okay, and you're going to plot here. So when this model try multiple guesses, then the curve for j theta as variable will look like this, like a parabola exactly, and it will exactly will have one minima because we are using only one feature whose degree is also 1. Okay, so what we need to do is to reach is at this minima using several guesses or iterations. And in every guess or iteration, we will be going to update the value of the theta using some strategy, right? Before moving forward, let me show you the visualization of this linear regression. Okay. This slide is visible. Oh, sorry, this video. Can anyone confirm?
Yeah, it's visible.
It's visible.
Okay, so initially, our slope value and the intercept value was 0. So this line is nothing but a horizontal line. And initially you will having some mean squared error value. So now let me play this video. So did you see what is going on? Mean squared error is reducing itself, and this line is shifting itself according to the distribution of the data. When you will be reaching at the perfect values of this theta naught and theta1, then the training of the model will stop because that is the minima that you have arrived. Okay. So for changing, the shifting of the line is taking place because of the variation in the values of the theta naught and theta1, right? So this is clear now why this is line is shifting, and we are going to update the parameters based on some algorithm which is known as gradient descent, and I will be talking it in some future slide. Okay. So here we have this hypothesis ready, and these parameters theta naught and theta1. Previously, I have shown you that theta naught was 0 just for simplicity sake, but now here it is not. So your cost function will be dependent upon both the values of the theta naught and theta1, that is slope and intercept. And for minimizing this cost function, you need to change both of the values of this theta naught and theta1. So with respect to the a single parameter, when you will plot this cost function, you will get this parabola, right? But when you plot in 3D, with first axis being your theta naught, and second axis there's theta1, and third being this cost function value. So you will be getting this contour plot in 3D, and it will be having some minima below here. At which your cost function value will be minimum for values of the theta naught and theta1. So what we need to do is to reach at this minima, right? So for that we are going to use gradient descent algorithm. So we have this cost function formulated, right? And want to minimize it. So the outline of this algorithm is to nothing but start with some value of the theta naught and theta1. and then keep keep changing these values, these parameter values according to the direction, such that you will ultimately reach at the minimum, right? So you need to change these values. So let's have a simple example here. Okay. So again, we are assuming theta naught value has to be 0 because for simplicity's sake, and this hx will be nothing but your equation, which is a line passing through the origin, and this will be your cost function. And as you can see, this cost function is directly proportional to the square of the theta, and thus this curve will look like a parabola. And we need to reach at this minima, right? So for that, what we can do is to start at some point. Let's say I begin at this point, okay, and I check what is the slope at this point. So slope here is negative. What that means, graph is going to decrease when you move from left to right. Like when you going to increase the value of the theta 1, the graph is going to decrease, the cost function going to decrease. So if the slope is negative at any point, you need to move forward, that is to increase the value of your theta 1. And let's say you are at this point, okay, here the slope is positive. So now graph is going to increase. So what you need to do is to move backward. That is to decrease your theta 1 in order to reach at the minimum point, right? So you can do that using this simple equation for the updation of the parameters, right? So this del is nothing but your slope or gradient. Let's say you are at this point, okay? So at this point, the slope is negative, okay? This alpha is the learning rate. I will tell you about it later, okay? So actually it is a positive quantity. So since the slope is negative, this whole quantity will become positive. Negative multiplied by negative, that is the positive quantity, okay? So your theta 1 going to increase with some factor, and thus it will move forward, okay? And let's say you are at this point, here the slope is positive. So this overall value will going to be negative, and this theta 1 will be updated as a less value than the previous one, okay? So clearly just you can take your time and look at this gradient descent step. This is
But
a gradient descent step.
I have a doubt
Oh, yes.
that j is proportional to theta 1 square. So as theta 1 keeps on increasing, j should also keep on increasing. So why is it like a parabola?
You know why y is equal to x square curve?
Yes.
And then it is simple for you.
Okay, so
That
it
is the
is
same curve.
okay.
So at any point, if the slope is negative, then you're going to move forward.
But
You
in
have
the y,
studied in 11th and 12th.
yes, but y equals to x square. The when x changes, it means when x comes from a negative to positive side, then the curve turns. But it is turning even in the positive side.
Yes, it will. Why not? Your y is equal to x square curve, you know now.
Yes.
That is the same here. Nothing changes here.
Okay.
When you increase the value of the theta, your cost function going to increase.
Yes.
So at any point where the slope is positive or negative, on the basis of that, we are going to take our step. So we won't directly jump at this minima point, right? So we need to start with some point. And then according to that point, we are going to take the next step.
No, but I mean to say that where j is minimum, why are we saying that point theta 1 equals to 0? Is it necessary that it will be minimum at theta 1 equals to 0 always?
No, it is not. It won't be. Actually, that is the point. We need to search for that minimum point, right? And this is the algorithm that works for that. Ultimately, you're going to reach at this point. In next slide, you will be getting a better understanding. I have make some animations for better understanding.
Okay. Okay, भैया.
And this differentiation, I guess you can easily understand. You have done this differentiation with respect to the theta 1, right? When this power going to come up over here, 2 will be divided, 2 going to divide, okay? That's why I have used this for averaging 2 by m. Okay, just for making simplicity, calculation easy here. So is anyone is having any doubt here? This is the like gradient descent step, idea of the gradient descent algorithm. Okay, I guess it is pretty easy to you. We have some idea about this algorithm, like, so let's understand the working in some points. So we are going to start with some random values of this theta1, okay, and then going to calculate the cost function at that point. And based on the cost function, you're going to calculate the gradient at that point. And it will tell you in which direction you should move in order to search for minima, right? And here the gradient is negative, right? So this will update the value of the theta1 with respect to this equation. Okay, so your theta1 will increase and will shift to this point. Okay, and again you're going to repeat these steps, these 2 and 4 steps. Again you're going to calculate the cost function at this point, then check the slope at that point, and according to that you're going to take your next step, like this and this and this, and ultimately you are going to reach at the minima. So when you are going to going to save the parameter, like at this point we are going to have this cost function value as minimum as possible. So you're going to this reach at this point and you're going to stop this training. Okay, take your time here and understand this steps, and if you have any doubt, please ask it.
Sir, what is alpha?
Alpha is your learning rate. I will tell you about it more in the further slides.
And
Like it is the
Bhaiya,
step size.
I didn't get that 4 point. Update the value of theta, that formula.
Uh, I told you earlier that you're going to reduce the error, right? And for that you need to shift your line according to the distribution of the data, right? It is clear.
Yes, yes.
Now this is like a simple formula that will help you to reach at the minima. So let's say you are at this point, okay? Now you don't know in which direction you should move. So you apply at this formula. You check what is the slope at this point, and it turns out to be negative, okay? Negative the slope at this point, and you're going to just put the value here. So negative multiplied by negative going to positive, and thus your theta1 factor going to increase with some value, right? So you're going to move from this point to this point.
Bhaiya, we can do it
Okay.
directly, that if we get negative, then we will increase the theta till we get slope as 0.
Like you have to increase with some, no, slope won't be zero. Like
At minima.
it will look here, like here for the theta1 value it is simple, but when there will be multiple features, then it won't be like simple to visualize or simple to understand. You can just do that slope at that point is zero with respect to a particular feature. It doesn't mean that this is the minimum point. With respect to the other parameters, the slope should be also be zero, and that won't be happen. I will tell you for the other parameters also. Here for the simplicity, I just choose only one feature, one that is theta1 variable. Okay, when it will be having two features, theta naught and theta1, these parameters, then it will be shifting in 3D, and understanding in 3D it will be a more typical. So just for now, you have this clear, right? No doubt here.
Yes.
Okay. So yes, previously what I told you is theta naught value was 1, right? That was the line which was passing through the origin, but now here it is not. So theta naught value is not 0. So what you need to do, your cost function going to depend on that value, theta naught and theta1, right? And thus you need to change these theta naught value and theta1 value simultaneously in order to reach at the minima. Okay, so now for that, calculating the slope at particular point, and for the updation of the particular parameter, you are going to use partial derivative. This function j, cost function, is the function of theta naught and theta 1. Now you're going to partially differentiate with respect to the theta naught, because you want to update that theta naught parameter, right? And similarly for this theta 1, you're going to equalize these value in some, store some these values in some temporary variable, and after that you're going to update this theta naught value. Okay, so this is the correct way for doing that. Like simultaneously update is necessary, because if you don't, that in your right side, that is an incorrect method. What you have done here is first you storing the new value of the theta naught in temp 0, and then you are re-changing the value of theta naught. But it is wrong, because you are going to use this theta naught value for calculating this function, this gradient also. So the changes that you have made in theta naught will going to reflect in this j. Okay, and this j will give a false estimation for the for these next parameters. So that is an incorrect way to do. So the correct way is to update the parameters is by using this simultaneously updation, right? This is clear now?
Yes, Bhaiya.
Yeah, can you explain this again?
As
The correct, incorrect part, I did not get it.
Okay, so I told you that you need to update the parameters of the theta naught and theta 1, like slope and this intercept parameter, just to shift your line towards the data distribution, right?
Yes,
Okay,
Bhaiya.
so for the updation of this theta net, what you're going to do first is to store in a temporary variable. Okay, because if you don't do that, like if you simply assign it to this theta naught value, then for updation of this theta 1 parameter, you're going to calculate this j value, right? And it is dependent upon the theta parameter, theta naught parameter that you have updated previously. So that change will reflect over here. Okay, in the updation of this theta 1, and that will bring you a false estimation of the next parameter, and that's why it is wrong. You need to simultaneously update the parameters and then assign the original parameters to it. Okay, did you get it?
Okay. Yes, Bhaiya.
Okay, this is in 3D plot, like theta naught is one of the parameter and theta 1 is the parameter. So here reaching to the minima is some typical thing, like you can do a slope equals to 0, because it will be respect to the parameter, but for all of the parameters. So let's say you began at this point, okay, and then you check for the steepest point in that location, and based on that you take your next step in search of the minima. Okay, you reached here, then you reached here, and ultimately you're going to reach at this minimum point. So that's how this algorithm works. You're going to update this theta naught and theta 1 parameter based on the gradient at that particular point. And for that, you are going to use partial derivative, because that cost function is of function of theta naught and theta 1. So for derivative, you need to find a partial derivative. Okay. And I told you what this alpha was, like that was the learning rate. Okay, learning rate, or you can say the step size. So when you're at a particular point, then you know the direction in which you're going to search for the menu using this gradient. Okay, slope at that point, you're going to have that direction. But by what factor you're going to increase or decrease your theta 1 value is totally dependent upon your alpha value. So this is the step size you need to take. Okay, if that value is always a positive quantity, and if you take it very small, then this gradient descent can be very slow. It will take very slow steps to reach at the minima. So the whole process will be very slow. And if you assume this alpha value to be too large, then this gradient descent can overshoot the minimum, and it will fail to converge or even diverge. So alpha choosing the value of the alpha alpha parameter is an important task that you need to do. Okay, that is done by hyperparameter tuning. But generally for these linear regression 0.1, 0.05, these values work fine. But they don't, then you need to use hyperparameter tuning. That will be discussed in further workshops. Okay. And alpha value is constant here. It is not variable because when you're going to approach your minima, this descent step and this slope at that point will be very less, and ultimately this factor that by which you're going to increase or decrease your theta1 value will be less. Okay, so that's why a fixed learning rate also work. When you approach the minima, the gradient descent step will automatically take some smaller steps. So there's no need to decrease alpha over time. The gradient descent step can over that, right? Take care of that. Okay. So till now, you have any doubt? Because everything we have learned, now we are going to sum up everything.
Yeah, please may you repeat that incorrect and correct ones, assignments. Incorrect and correct.
Okay. So what we need to do is to update this theta naught parameter, right? And your cost function is dependent upon that. So when you are going to calculate this temp one variable, a value, like here, if you assign the updated value theta naught, okay, then and then you calculate the gradient at that point. So that would be a false estimation because you have updated your theta naught parameter, right? One parameter has been updated and you are using it for updating another parameter. That is not true. That is a false way to do. You have to update both the parameters with respect to the previous values. Okay, and then you are going to assign it. That is the thing you need to do.
Okay, Bhaiya. Thank you.
Right? So I guess everything is clear till now. Anyone is having any doubt? Now let's see this linear, like a sum of everything that we have learned. Okay, previously we are having only one variable x, and thus I told you that equation of the line, that is y is equal to mx plus c, can fit over that data, right? So based on that assumption, I end up with this hypothesis value, nothing but the equation of the line. Okay, and then I want to judge like which line is a good fit or not. So I will be doing that based on the error I am getting from a particular values of the theta naught and theta 1, right? So this is the cost function that we got. And based on that cost, we are going to update the values of the parameters that you have because of the slope or in search of the minima point, right? So theta naught and theta 1 are the variables, are the parameters here for this equation. So we put both these values, theta slope value and the intercept value, using gradient descent step that I told you earlier, right? And derivative, I guess, will be clear to you guys because all you are math students. So this cost function was of the function of theta naught and theta 1, right? So I just replaced this j value here with this cost function, right? And then I expand this hypothesis, which was this equation of the line. Okay, now I want to update my theta naught parameter. Theta naught parameter, and for that I need slope at that point. And I will be doing that using partial derivative. So I'm going to differentiate this above equation with respect to theta naught. And differentiation is easy. This is understandable to you guys. Okay. For theta naught, will nothing is here. Only one will be left here when you will differentiate it. Power differentiation, you know. And when you update this theta 1 variable, like calculate the partial derivative with respect to the theta 1, then you are having this factor x1, because everything other than this theta 1 parameter will be constant. So your 2 will come up here and cancel it. the same will be repeated. It will go inside that. Theta naught will be constant, yi will be constant. Only this theta 1 will be a variable because of the we are derivating it with respect to the theta 1, and thus you will be getting this x1 parameter here in multiplication. This partial derivative is clear or not?
Yes, Bhaiya.
Yes. Okay. And that is the gradient descent algorithm. Okay. Ultimately, you are going to start with some random value and then apply this algorithm, and it will eventually end up at some minimum point. Okay. So what we have learned earlier was for only one feature, right? So depend on only one feature. It will be dependent on multiple features like this number of bedrooms, floors. I just want to say that there will be multiple number of the features for this target variable. So in that case, nothing will be changed, only some minor changes. So your previous equation was the line, but now it will be changed. It will be in form of this equation. Okay. Hypothesis is clear here for multiple features. It was the same the previous one, but because of you having multiple features, you were going to find multiple values of the parameters, this theta 2, theta 3, and these are some external extra parameters that you need to find. Okay, so this is the hypothesis equation. Clear to you guys?
Yes, Bhaiya.
Okay, thank you. So that was the hypothesis value on this equation, theta naught multiplied by x0 and this blah blah blah. Okay, so for making calculations easy, we are going to use vectorization, matrix multiplication. Okay, so I wrote here like this hypothesis value as theta transpose multiplied by x. So your theta transpose is nothing but this matrix of these parameters, theta 1, a column vector, right? And x is your another this feature vector. Okay, and when you going to multiply it, theta transpose multiplied by x, this will be your final equation, the final hypothesis, right? Am I disconnected?
No, your your things are visible.
Sorry for the disconnection. It's been raining here for 3 days, the last 3 days. Where was I? So I was explaining this hypothesis, right? So am I audible right now?
Yes, Bhaiya.
Okay, so this hypothesis is a theta transpose x, where your theta is nothing but a column vector. Okay, and then x is your feature vector. So when you're going to multiply both of them, that is theta transpose multiplied by x, then you're going to have this equation. And then you're going to have these parameters as a theta vector. Okay, theta vector is a vector of the parameters. So your cost function will be updated. It will only dependent upon a vector of the theta. Ultimately, it is going to depend upon these theta naught, theta 1, and so on. Yeah, right? And then your gradient descent step will also going to be updated. So previously, when there was a line which was passing through the origin, so theta naught was 0 in that case. So in that case, you are only going to update theta 1 as the value. Okay. And now after that, I assume theta naught value is what, not 0. So in order to reach at the minima, you're going to change both theta naught and theta 1 value, because your cost function was the function of theta naught and theta 1 parameter, right? So in multiple regression, your cost function will be dependent upon theta naught, theta 1, and so on, number of the features that you have, right? So you need to update that also in order to reach at the minima. there are multiple features. It is harder, difficult to visualize here. So I explained you in form of the 3D or 2D for only one variable, and now here I have just generalized everything for n number of the features. So this is right, nothing but the this same what was it? One feature, only one variable was there. So that was our previous step. Now we have multiple features, so you need to update multiple values, theta naught, theta 1, so on, using partial derivatives. So that is also easy. So this is it for linear regression, and if you are having any doubt, please ask here. This multiple regression is clear to you guys? Same, it is same like previous one.
Yes, Bhaiya.
Okay. Thank you. So any doubt right now?
Bhaiya, in matrix slide, please show me matrix slide.
So yeah, it is.
Sir, the matrix of X, it should be horizontal, not vertical.
Do anyway. That is nothing matters. Or you ultimately you are going to end up with this value theta naught. This when you will multiply it with variable vector. Okay. So you can also take it as a row vector, but you need to perform this matrix multiplication. So you know, if first has the dimension n cross m, then another must have dimension m cross x something. Okay. One should be having a common dimension, right? For performing this multiple multiplication. So that is what. So do any way you want. Just end up with this value, this equation.
Okay.
Okay, I guess no doubt is there. So Ujjwal will be taking and he will be understanding, explaining you this logistic regression, right? So Ujjwal, you can present your screen now.
Screen visible.
Yes, yes, it is visible.
Let us begin with a logistic regression. So we do not have many much time, so we'll not go in deep calculations. So now starting with we will basically discuss three parts. What is logistic regression? Why we use logistic regression, and how it is different from linear regression. So let us start with what is logistic regression. So logistic regression is basically the tweaked version of linear regression, wherein at the output of linear regression, a sigmoid function is applied to make a binary predictive model. So basically, it means to say that it is only linear regression, but at the end we apply a sigmoid function. As you can see, this is basically a sigmoid function. At the end, we deploy a sigmoid function, and we take input as x1, x2, x3, and theta 1, theta 2, theta 3 are the parameters. We put them in a sigmoid function, and we get an output as happy or sad. Like we get output between 0 and 1. So it is nothing, basically a linear regression, but we add sigmoid function to it. And now coming to, so basically it is a classification problem. It is though its name is linear logistic regression, but it is basically a classification problem. It classifies whether it belongs to a positive class or a negative class. Like for email, you can say spam, not spam, transactions, fraudulent, yes or no. And for tumor, it is malignant or benign, like very serious or not. So these basically logistic regression deals with classification. So this is all about what is logistic regression, like how it is different from linear. In linear, we basically deal with lot of values, not like 0 and 1. But in case of logistic, there are binary classification and various multi-class classification also, but there is classification, not regression. So this is all about logistic regression. Now coming to why do we not use linear regression for classification? So let us say if we what happens if we use linear regression. So let us say we have a plot like this. So here are the tumor sizes. The x-axis corresponds to tumor size, and the y-axis it shows whether it is 0, that is it is not serious, or 1, it is very serious like malignant. So there are a lot of cases. So if we draw a line and try to differentiate it, like whether it is malignant or not, uh, we can say that if h theta x, the function, if it is greater than 0, then we can basically say we can basically classify it as 1. But if it is less than 0.5, then we can classify as 0. So where is the problem with linear regression? So let us say we have a new data set. As we can see here, we have a new data set here. So if a new data set come, so what happens? First of all, the error goes very high. This is the error now. So this error goes very high. So that is one of the problem with linear regression. And what happens if the error goes high? Whenever the error goes high, what it tries to do linear regression? It tries to find a new function such that error is minimum. So what will happen? This line will, let me change the color. So what happens? This line basically goes now here. So this line converts to this line. So what happens now? Let us say we are dealing with this case. Like we can say, okay, let us wait. Let me draw better line for better understanding. So let us say our line goes like this. So it has a less error. So for now, let us say we have a point like this. Previously we had a point like here. So for previous line, we found it that it was malignant, it was very serious. But for new line, we can say it is less than 0.5. So we basically say that it is not serious. So what happens that what previously was malignant now became benign. So this is a serious problem with linear regression. It basically alters all the data set. Like what was showing previously 1 now shows 0. So this is one of the major problem with linear regression. So yeah, so as you can see in it, there is a large residue, and large residual, hence abrupt change in regression function. So function will change abruptly, like line will change to here. It will not remain same. So all the inputs and outputs will alter. So this is one of the major problem with linear regression. And also we wanted the output to remain between 0 and 1. So that basically we wanted a probability, like how much it is probable to be malignant or benign. But if we plot a line, and let us say our point is here, let us extend it. So if we just go up and extend this line, so it will be very high, not 1, it will be much larger than 1. So these are also one of the problem, though our labels are only 0 and 1, but we are getting output as 1000, 2000, and so on. So this is not something we wanted. So these are basically the two problems with linear regression, why due to which we use logistic regression. Now anybody has any problems till now, like why anybody not able to understand this graph, like these all things, they can ask. I can give you another example also, or should I proceed?
Understood, Bhaiya.
Okay, anybody having any problem, just speak and stop me at any time. So now coming to what is a logistic regression model. So basically what we wanted that all our values to be between 0 and 1. We wanted to squash all the values. So like this, you can see what we wanted h theta x greater than equals to 0 or less than equals to 1. So what we basically do, we assign a new function to it. H theta x basically original it was this one, but now we assign a g before that. So this is a new function. This whole a new function, and this function basically is this. So what it does, it basically gives all the values between 0 and 1. As you can see here, this function for whenever z is greater than 0, it outputs values greater than 0.5, and whenever z is less than 0, that is negative, it outputs values less than 0.5. So this basically squashes all the values, all the real values to between 0 and 1. So this is one of the major benefit of this function. That is why we use in case of logistic regression. So this is basically our new function. And here what we were using this is basically z. It was originally h theta x, but now we have converted the whole new function, and it basically becomes a new function. And the h theta x, this part comes here. This is z. So this is our new logistic regression model. Anybody having any doubt can ask. You can ask any in between. Now I am continuing. Now coming to decision boundary, like how we deal with decision boundary, basically how we differentiate between positive and negative classes like 0 and 1. So basically we try to what we try to do is, whenever h theta x gives us values greater than 0.5, we assign them 1, and whenever it gives values less than 0.5, we assign them 0. So basically it is a type of classification, like we are assigning 1 and 0 according to our needs. Like we have set this might change, but basically we take this only, like 0.5. This is basically the edge between the positive and negative class. Now let us take some examples of decision boundary, like how you understand the decision boundary. So let us understand this. So let us say that we have a function theta naught plus theta 1 x1 plus theta 2 x2. So, and this is the data set, like this is the one class, positive class, let us say, and this is negative class. So how we will differentiate? So we have to basically we try to get parameters theta 0, theta 1 and theta 2 such that we are able to differentiate it. So let us say the values are -3, 1 and 1, that is theta naught is -3, theta 1 is 1 and theta 2 is 1. So what happens, this function becomes -3 plus x1 plus x2. So basically it is a line like this. It is basically a line like this. So whenever we take this point and put in this line, line equation, will get greater than 0. And what when g of z, when z is greater than 0, what it gives? It gives basically greater than 0.5, as you can see in this slide. Like whenever it is greater than 0, it gives somewhere here. So basically what we are getting, whenever we put in this equation and it is greater than 0, g of z is greater than 0.5, and basically that corresponds to positive class. And whenever it is less than 0, it basically this whole thing is less than 0, this is basically less than 0.5, and that corresponds to negative class. So this is basically how easy the sigmoid function has made the classification. So it is one of the huge advantage, and you can also see it can easily classify the positive and negative classes. So this is one of the example. And also now coming to this part, like here is also a data set, and this is basically a function. So can anybody say like what the decision boundary will look like? Anybody having
A
any
circle.
idea? Yeah,
Circle.
basically, yeah, it is the circle. Like you can see here also, like when we assign theta naught -1, theta 1, theta 2 0, and theta 3, theta 4 1 1. So what it makes a circle like this. It makes a circle of radius 1. So what happens whenever we put these data set, this value, it comes less than 0, which basically means g of less than 0 means less than 0.5. So basically we get negative class, and whenever we put these all data sets in this, we get a value greater than 0.5. So g of we get a value greater than 0. So g of greater than 0 means greater than 0.5. So basically we classify them as positive class. So this is basically how the sigmoid function works, like how it differentiates the positive and negative classes. So I hope everything is clear till now. Now let us move to what is cost, means how we'll get the parameters, like how to choose parameters theta, because they are mean, like here we are telling -1 0 0 1 1, but how do we get it? And that is an important part. So let us see like how we are getting it. So first let us say what is the problem with linear regression cost function. Like the cost function was this. So 1 upon 2m, like this was the cost function. So let us say replacing this, we just put cost of h theta x comma y, and now equate these two, like this one and this one, you just equate. So what happens, it basically gives this equation if you equate these two also. Like for particular xi, cost of this is equals to half of h theta minus y ka whole square. So this is what we get. So what happens, this is basically, and when we'll substitute h theta x, what is h theta x? You all know it is basically a sigmoid function, like 1 upon 1 plus e and k power minus x. So it is basically a sigmoid function, and when we will put in that, so we will get a very bad function. Means that is not something we want. It means that is not linear. We'll get a very non-convex function. And when we'll put this in, basically when we'll put this here in j theta, what we'll get? We'll get basically a different this type of function, this function. And what happens in this? There are a lot of local minima. There is lot of minima. Like before coming to this, basically we are dealing with lot of local minima, so we'll never be able to reach here, because when we'll find here and we'll go here, we will get a larger value. So we can assume that this is our global minima, but that is not the case. Global minima is here. So that is the problem with linear regression cost function. We wanted something like this, but we cannot get something like this with the help of linear regression function. So are you able to get this, like why we cannot use linear regression cost function? Because the ask.
No, sir, I didn't get this. Why are we not getting this convex curve in this case?
Means that is experimental, that you will put and you will plot the graph, you will get this type of curve. That I means this is the type of graph that you get. If you will estimate this, you will put this in that, because that time it was a linear function, linear or something, say it was a function of, it was not like that, it was not. But in case of logistic regression, it is something like 1 upon 1 plus e power minus x. So this is something what changes, due to which it loses its convexity.
Okay, bhaiya, got it.
Okay. So this is the problem with linear regression cost function. Now let us come to what we can do with logistic regression cost function. So one of the best cost function is basically for if the input, the label is y, if the output, if y is 1, then we can assume the cost function is minus log of h theta x, and if it is 0, we can assume it is minus of log 1 minus h of theta x. So let us say y. So let us consider first case, if y is 1. Y means we have given the output, that label is y, and we wanted that our predictor predicts close to 1, that we wanted 1. So basically minus log of h theta, what it looks like? It looks like this, like it basically it goes 1 to 1. So what is happening basically, whenever if y is 1, so we wanted 1, so cost is 0. If y is 1, h theta is 1. So if we put 1, and if our model predicts 1, so what is our cost? Our cost is 0 basically. That is all we wanted. We wanted a 0 cost if our system predicts correctly. But let us say if the output is 1, but our system predicts 0, then cost becomes infinity. Like if you put 0 here or something close to 0, it will shoot up to infinity. So this is a very good function. Like whenever it gives us 0, the cost tends to infinity, and whenever it gives 1, the cost is 0. So this is something we wanted. So it works correctly for y equals to 1. Let us say when y was 0, that is the output was 0. So if y was 0, so what happens? If you will plot this function, it will look like this. Like if it is 0, like this. So it will, for 1 it will not, for 1 it will shoot at infinity. Now let us say our output is y is 0 and h theta comes 1. So it becomes basically 0. Now for 0, it basically shoots up in high infinity. But whenever h theta gives 0, it is basically 1 and it comes down to 0. So basically cost is behaving the similar way we wanted. Like if y is 0 and h theta is 0, we are getting 0 cost, and if y is 0 and h theta is 1, we are getting infinity as cost. So this is how cost function works. So anybody having any doubt in cost function, like not able to understand, or I am a bit fast, you can tell me, I can explain you. Okay, so I'm continuing. I hope you don't have any doubt. If you are not able to understand it, just ask anything you want. Now coming to simplified cost function. Just wait a minute. So now coming to simplified cost function. So we wanted like for y equals to 1, for y equals to 0. We are separating two different cases, but we wanted to combine them into one. So what we can write? We can write as cost h theta x y is basically minus y log h theta x minus bracket mein 1 minus y log of 1 minus h theta x. So what happens this is basically a equation that simplifies down to this. If y is 1, it becomes simply this, and if y is 0, it becomes this. So basically it is a combination, nothing more than that. That is just an imagination, that is nothing rocket science. So with the help of this, we can, for y we can get this, and for y equals to 0 we can get this, and it is basically a combination. For more clarity, this is basically what we get at the end. This is like yi log of h theta xi, and plus 1 minus yi log of 1 minus h theta xi. So are you able to understand it? Like, can any
Yes.
can you tell me what is yi here?
Bhaiya, Vaya is the corresponding value of that.
Yeah, it is output label.
Yes, that graph which the line or something which we are drawing. That if we put a value x, then the corresponding value of y.
This is basically the data set. This is what yi is. Basically we are given it, we are not finding yi, we are finding this one. This is something we are finding. Okay,
Oh, means
are you?
y is y.
Hello, hello, is this clear? uh, are you able to understand that what is yi and what is h theta xi? Hello, is my voice visible? I will is my voice audible? Yeah, ask.
Yes, Bhaiya. So basically, we can say that that h theta x is the regression model.
Yeah, basically it is a regression. It was something we are getting basically in the regression model. This is basically the output we are given. We are given the data set na, x and y.
Yes, yes.
Yeah, that is, it is that. And our now it, in this case our model is in learning phase. So this is something given to us, and this is something it is predicting. That is the difference.
Okay.
When we are in training mode, we will not get this one yi, but when we are testing mode. But when we are in training mode, we will get this yi. These are the labels, and this is something we are predicting, h theta xi. Okay.
Yes.
If you have any doubt, any doubt, you can ask me uh, from anywhere. So now coming to gradient descent, like why do we need gradient descent? Because we want best values of theta. Like theta is the main parameter which decides the decision boundary. So now we want what we want that cost functions to be minimum. So that is exactly similar to regression. Theta j equals to theta j minus alpha delta by delta theta j. That is basically the cost function. So are you able to get this equation? It is same as linear regression. Anybody not able to understand this equation? So this is basically, it is trying to minimize, it is trying to get parameters theta j such that the cost function is minimum. That is what it does. So it is similar to the linear regression. And what happens here, we basically put the values of j theta in it, and when we simplify it, the simplification is means it is very easy, but I cannot show you here, but you can do it yourself. Means it is very easy. So you will get this value after simplification. When you will do it, you will get this value. So this is something you will get after simplification, and it basically looks like similar to linear regression. So in this way, we update the theta j value, and finally we put it there, and we get the cost value. Like if cost is very less or it is minimum, then we fix the theta j value. That is our answer. That is our theta j, and that we'll use for our model. So this is something we do with gradient descent. Now I hope you are clear up to this. Like now we basically comes to multi-class classification. Like for multi-class, it basically is when you are given a lot of classes. Like here you can see work, friends, family, hobby. There are 4 labels. Not ill, cold, flu, there are 3 labels, and sunny, cloudy, rain, snow, there are again 4 labels. So this is basically multi-class classification when you have a lot of classes, not only 2 but more than 2 classes to identify. that is multi-class classification. So what we use in that, in case of multi-class, we use one versus all concept. What it does is, we basically, let us say we are testing for triangles. So for rest of them, we assume they belong to one class. Let us say they belong to like circle. Let us put circles to them. So basically, we came down to two classes. We basically came down to binary form. So this is what we do in multi-class classification. We apply the one versus all concept. So here we will here we'll train three classifier. Like first one is s theta 1x, which will basically tell what is the probability that it will be a triangle or not. And second one is h theta 2x, which will tell whether it is a square or not, how much, what is the probability that it is a square or not. And h theta 3x, it will tell whether it is a cross, how much probability is whether it is a cross or not. So basically there are three classifier, three different classifier for three classes. And how will what is our final approach? Let us say we are given a new input x, and we want to know that whether it is a triangle, square or cross. So basically we'll run through all the three classifiers. Like we'll run through all three classifiers, and in which one it will predict the maximum probability. Like let us say for square it gives 0.95. So yes, it is our class. So we'll assume that the label will be square, the output will be square. So in this way we deal with like multi-class classification, one versus all approach. Now I think now it comes to an end. Anybody who wants to ask any questions, if you have not understood anything, you can ask me, or I'll unshare it. Okay, I'm unsharing it. So Payal or
Yeah.
Tarun, you can continue.
They're missing. Hello. My screen visible?
Yes, you
Yes,
are
yes.
audible and visible.
So now you people have learned the two models, which are linear and logistic regression. Now I will deal with some of the problems that we may face while training these models. And those are overfitting and underfitting. Like these are some of the fundamental concepts in machine learning, and they are very important because they explain the state of a model based on their performance. Okay, so first of all, I will tell you what is overfitting. Like most of the time, overfitting is the main cause behind the poor performance of machine learning models. Like here, you can see in the image, there is a bed which is totally confined to a person's sleeping position. So overfitting is similar to something like that. Like overfitting occurs when a model tries to learn the pattern or noise in data to such an extent that it hurts the performance of model on new data set. Like that model is closely fit on the training data set only, and whenever it sees any new data, it will give a wrong prediction. Like okay, so in technical terms, you can define overfitting as a when the like overfitting will be occur overfitting will occur if the model or the algorithm shows a low bias but high variance. To understand this to a better level, I will explain what are these terms bias and variance. Okay, so what is bias? Like here you can see in the 2D plot, in first image the curve is not looks like a not a good fit to the data. Like here it can be said that model has a very high bias. When the model has a very high training error, it's a sign that it has a high bias. Okay, so a bias is mathematically expressed as the squared difference between expected predicted target values and the true target values. And it is squared to penalize more heavily on the predictions that are farther away from the true value of the target. A model with a high bias will pay very little attention to the training data, and it will oversimplify the model. Like I will explain with you people with a simple example. Like if you are, let's suppose you are working with a classification model, which like a classification problem in which your model predicts whether the given image is of a cat or a dog. Like for a human, it's really easy. Like you can easily tell whether it's a cat image or dog image with 0% error. Like we will assume that human error in this case is 0%. And suppose you train a model and its training set error is 16% and test set error is 17%. Like this looks like an algo which is not doing very well on training data set. And also test data set error is very high. So like here the performance of test data set is only just 1% less than the training set. So we can say that this algorithm has a problem of high bias. Okay. Now coming to variance, like we have learned what is variance in our 11th, 12th, and also now the second year rights might be having the course called MA202, where they might have learned this term. Okay, so variance is a measure of how far off each prediction is from the average of all predictions for the testing set. Okay, like it is also squared. Like here you can see the variance definition. Like it is also squared to penalize the predictions that are farther away from the average prediction of target. A model with high variance pays lot of attention to the training data. Like as in that overfitting image that I shown here, you can see that the learning curve is trying to pass through all the data points. Like it's paying a lot of attention to training data, and it does not generalize well on data that it hasn't seen before. So in third image, if you can see, like the data fits perfectly, but it doesn't look like a good model either because it's clearly overfitting. Like we can say that a model has a high variance if training set error is lower than the test set error. This tells you that you are doing very well on training data set, but you are doing relatively poorly on the test data set. Okay, and the middle image is it looks like a reasonable fit for the data. Like it might be any model or algorithm with medium level of difficulty. Now coming back to the variance overfitting, you can easily tell whether a model is overfitting or not just by measuring the training and test set accuracies. Like as I said earlier, our model is clearly overfitting if it has low bias, that is low training error, and high variance, that is high testing error. Okay. Like the problem of overfitting mainly occurs with nonlinear models like decision trees or some complex models like neural nets. But sometimes in linear models, we might have to deal with this problem. On the other hand, underfitting is on the other hand, if model is performing poorly over both the data set like test set and train set, then we can call it that as an underfitting model. Like this model neither learns from the training data set or nor generalizes well on the test data set. And we can easily detect whether our model is underfitting or not just by looking the performance metrics of that model. And in case of underfitting, the only solution is that we should try some other models. Like if our model is underfitting, then it's not a good fit for the data set or the problem we are solving. Okay, so if you try some new model, this will certainly give you some good results. So both the overfitting and underfitting leads to poor predictions on new data sets. Okay, so let's understand with some example. Like here you can see that the figure is showing learning curves of 3 different models. Hello.
Payal, can you increase the size of the screen?
Is it not visible?
For me, it is like now it is fine.
Oh, sorry. Is it better now?
Yes.
Okay. So here in the figure, you can like I have in this this figure shows the three plots of different models which are used for predicting housing prices problem with different number of inputs. Okay, below each image there is a hypothesis function for each model depending upon the number of input features. like uh, by looking at the image you can clearly see that the model 1 is underfitting and model 3 is overfitting. Like if you see the first plot, we can understand that model is not fitting well on training data at all, and so this model will have a less train and test accuracy, and hence it will have a high bias. And if we take a look at last plot, here we can see that this curve seems to do a very good job. Like it's passing through all the data points. Hence, it will have a low bias, that is low training error, but a high variance, like that is a high testing error. So the problem of overfitting comes when we have too many features, such that so that the learned hypothesis may fit on training data set very well. That is, your cost function may actually get close to zero or maybe even zero sometimes. So whenever your cost function gets close to zero, like you will get a learning curve like the third one, which is passing through all the points. Like it's trying really hard to fit the training set so that it even fails to generalize to new examples. Like new examples here refer to the data that model hasn't seen before, or which is a new trait. So now we will take a look at how can we solve this problem of overfitting. Okay, so there are several solutions, and I will be discussing some of them. Like the first solution can be reducing the number of features. Like if we have too many features, our hypothesis will become too complex, and it will make our model prone to the overfitting. So what we can do is we can manually select some features that are not relevant to the output, and we can delete them. But we should keep in the mind that whenever we reduce any feature, we lose that much information, and anybody don't want to do that. Like right. So if we don't want to reduce any feature, the another solution can be regularization. Okay. So So what is regularization? Regularization is one of the most important concepts in machine learning, and this technique we use to reduce the overfitting problem and get these learning algorithms to work much better. Here we can keep all the features, like unlike the first solution I discussed. Here we don't have to reduce any features. We can keep all the features, and it will work well when we have a lot of features and each contributing towards the prediction of y. Okay, so what we do in a regularization? So in a regularization we basically add a term called penalty term uh, to complex model in order to avoid overfitting by reducing the variance. So basically, this technique forces us not to learn a very complex model. Here, actually, what we do is we penalize the model parameters. For those of you who don't know model parameters, like as Rishabh told you, those theta 1, theta 2 parameters, they are the variables your algorithm trying to tune while building a accurate model. Okay, so basically we penalize these model parameters such that they become very small and which result in simpler hypotheses. And hence our model will be less prone to overfitting. To understand it better, like let's consider the linear regression cost function. Yeah, so here you can see that I have taken the browsing a price prediction problem. Like suppose we have 100 features, like the 100 features on which we will be training our model. Like so, suppose the 100 features be x1, x2 up to x100, where x1 can be the size of the house, or x2 can be the number of floors in that house, and associated with all these features, let's consider there are theta 1, theta 2 to theta 0, theta 1 to theta 100, 101 parameters, okay, associated with each feature. So when we have too many features, it's really hard to decide like which one are relevant to the, which one will be relevant to the y value, okay. And also among the 100 parameters, we don't know which one to tune. So in regularization, what we will do is we will modify the cost function to shrink all the parameters. Like we are now not just tuning a single or reducing a single parameter, but we will actually shrink all the parameters. Like here, I have written, I have added the cost function for linear regression without regularization, and after modification, uh, that after adding regularization, our cost function will look something like this. Uh, like I have added this term lambda into summation of theta j square. Okay. So here this last term lambda into summation of theta j square. So this last term is called as regularization term, like where lambda is the regularization parameter. So this term will shrink or penalize the parameters like theta 1, theta 2 to theta 100. Like here we are not going to penalize the theta 0. Okay. So I will tell you the reason. Like here what lambda does is control the trade-off between two goals, like between the goal of fitting training set well and keeping the parameters small, and thus keeping the hypothesis relatively simpler to avoid overfitting. Like if we keep the lambda very high, okay, so what will happen is the parameter will be penalized to a higher extent. Like all parameters may get reduced to zero, and our hypothesis may look like this h theta x is equal to theta naught, like theta 0, like only one parameter, and this will result in underfitting. Like the learning curve will be just a horizontal line to the data. So we should take some care while choosing the correct value of lambda. Otherwise, the regularization we are going to apply will definitely fail. It will not work. So if we take a look at the gradient descent of linear regression, here the first image, I haven't changed anything. Like this is the normal gradient descent that we learned just now, and here the reason behind writing the update for theta 0 separately is that for our regularized linear regression, we penalize parameters like only from theta 1 to theta 100, but we don't penalize theta 0. So while modifying this regularized linear regression, we will treat theta 0 slightly differently. Okay. So when we implement the regularization, like here you can see, we will end up a gradient descent for trying to minimize the regularized cost function. So this term in purple bracket, if you can see, with calculus, it's possible to prove that this term is the partial derivative of j theta with respect to other theta values. Okay, so like this term is partial derivative with respect to j theta, and using a new definition of j theta with regularization term. Okay, like if we take a partial derivative of this updated regularization, linear regression cost function, then we will get this result. Okay, So, and on the top in cyan bracket, will be still the partial derivative with respect to j theta with respect to theta 0. So now if we group the terms which are dependent on theta j, we will get equation like the below one, this one, where like j theta is equal to j theta into 1 minus learning rate into lambda by n, and this is the normal update like linear gradient descent term which we have seen in linear regression without regularization. Okay, so here the coefficient of theta j is a really pretty interesting term. Like it's going to be a number that is less than 1. So why? Like usually your learning rate will also be less than 1 and the m value will be large. So this coefficient will become pretty small. Okay, so at every update we are multiplying theta j with a number which is less than 1 and hence shrinking the parameters, and then we are performing a similar gradient descent update as before. Like if you see the gradient descent without regularization, here we are wait a minute. Yeah, so here we are just subtracting the partial derivative. So this is both will be similar. Okay, so now similarly, if we take a look at cost function and gradient descent for regularized logistic regression, it will look like this. It looks exact, not similar, but with a slight difference. Like it looks slight different to the uh, gradient descent we had in linear regression, but it's not the same. Like because the hypothesis defined for logistic is something like h theta x is equal to 1 by 1 plus e power theta t x, like it's a sigmoid function. Okay, so that's the gradient descent for logistic regression. Okay, now the last part is there are two types of regularization techniques. First one is ridge regression. It is also known as L2 norm or L2 regularization. Like here it adds a penalty term which multiplies lambda with the square weights of each individual feature. Like after adding the regularization term, our optimization function will become something like this. So in this equation, the penalty term regularizes the coefficient of model, and hence the ridge regression reduces the magnitudes of coefficients that help to decrease the complexity of model. Okay, and the second type is lasso regression. It is also known as L1 norm, and like it's similar to ridge regression except that the penalty term here includes the absolute weights instead of square of weights. So after adding the term, our optimization function will become something like this. Like this is normal RSS plus the lambda into the sum of absolute coefficients. Okay. So the L1 penalty has effect of forcing sum of the coefficient estimate to be exactly equal to 0, which means that there is a complete removal of some of the features. So therefore, this lasso method will also help us perform the feature selection, um, and it is said to yield sparse models. Okay, like which are not too much complex. Yeah. So these are some of the regularization methods, and we also have some more, but we will be discussing them in neural while when we will learn neural networks, and those will be covered in the next workshop. Okay. So yeah, this is all from my side. Tarun. Are there any doubts? Like you can easily, you can ask me any doubts if you have. Hello?
Yeah, you're audible.
Okay. I guess there are no any doubts. Okay.
Yeah, is my screen visible?
Yes.
Yeah, okay. Okay, so now I'll be just giving a brief overview of like how to implement linear regression using Pytorch without using any inbuilt Pytorch, let's say functions other than AutoGrad package. So let's start by importing. And many people are asking about GPU, so you can use your GPU using in Colab itself by changing your runtime and then selecting GPU over here. Yeah, and you'll have only a limited, I guess, 12 or 8 hours of GPU per day. And if you're using only CPU, that is none, then I guess you have unlimited. Yeah, so PyTorch we actually use because it automatically helps us calculate the gradients with respect to these weights. So we need not write those derivatives with respect to the functions. So if you want to calculate gradient with respect to a function, with respect to a variable, then while creating the variable, we just put requires grad is equal to true. So here x will be our input, w will be our weights, and p will be our bias. So we'll be calculating gradients with respect to both w and p. And yeah, so we've learned that linear regression is just a linear combination of our weights and the coefficient of our inputs, and the coefficient will be our weight. So here the coefficient is b and w and b. Yeah, for coefficient of let's say for b, we'll assume that there's a input of 1 and b's coefficient of 1. So yeah, in PyTorch also we can calculate the function y is now a combination of variables which require grad. So even this function will support calculating the gradient. So here it's the gradient function will be with respect to add, and we can actually calculate the gradient by just calling y dot backwards. That will help us calculate the gradient. So here you can see like when we call calculate with respect to w, we just call w dot grad, the answer will be 3. So you can see here the gradient with respect to w will be just x, and x is 3. So we get, and with respect to b, if you're calculating, we get 1. Yeah, so with respect to b we just get 1 over here. So how is it doing is yeah. So PyTorch will have its internal representation of variables with having some attributes. So it will have attributes like data, which contains what the number is, what the variable is storing, requires grad, whether the variable requires grad or not, gradient or not, and the gradient of the variable which we will calculate. And grad function is that's what we saw for y will be add backward, because it's just we're adding these variables x times w plus b, and for z will be x times b because we're just multiplying them. So is leaf is whether it's the end of the gradient, like we need not calculate further more. Yeah, if leaf is true, then the gradient ends over there. So let's assume we have created our intermediate variable z. So x times w will be z, and then we've just multiplied it with this function. And now we are adding z with b. And b also will have its gradient true, and it will be leaf node. Same with w. The gradient will be true, and it'll have a leaf node. And then we'll add, we'll get y. So this part where we are moving forward is called forward propagation. Yeah. And when we call y dot backwards, actually Pytorch creates its own representation of how to calculate a gradient. So add function have its corresponding function or object called add backwards, and multiplication will have the same thing. So when we call y dot backwards, it starts calculating the gradient with respect to these yeah, with respect to variables whose gradient was true. So with respect to dy by db will be 1, then with respect to z will also be 1, and then for multiplication in backwards with respect to w we'll get 3, and with respect to x we don't need to do because the gradient is false. So now, so yeah, this part where we move backward is called back propagation, and so we can like imagine there are two steps which is divided like this. So when we call w at grad actually starts with y and keeps on calculating the gradient until it reaches our variable w. So in that we have these derivatives like dy by dy and dy by dz and dz by dw. So when we multiply all this, we get dy by dw, and at the end we get answer as 3. And the same thing we'll be doing for b, and for that we get answer as 1. Yeah, so this is how Pytorch calculates the gradient. Now let's write a program for a problem statement. So here we have three variables: temperature, rainfall, and humidity, and we have to predict the production of apples and oranges. So here, instead of predicting one variable, you have two variables. So yield of apple and yield of orange. So we have to just make a linear combination of these with their weights, respective weights, and we'll be done with that. So let's say our inputs. Yeah. So here each row is an input for us, and we have 5 inputs, and each column like the 73, 91, 87 is the temperature, rainfall, and humidity. And the targets here, so each row will be our outputs, and each column is for apples and oranges, etc. So then we'll convert our numpy arrays into torch by using from numpy arrays, from numpy, and we'll get into tensors. Okay. So now to write the equation to initialize weights and biases. So this will be a 2x3 array, and bias will be a 2x1 array. So we actually don't know the weights and biases, right? So we'll just initialize them randomly. So each time I run this, I get a different random value for weights and biases. So, and yeah, we'll let the requires grad be equal to true for both of these. And now to calculate our y value, we can actually use these matrices itself. We can use matrix multiplication to find, as they have told earlier, this will be much faster than using your for loop. Instead of multiplying each row with the respective weights and adding biases, this will be much quicker, and this will be much more efficient. So in Python, we will use this at symbol. This will calculate matrix multiplication, and this star symbol which you use for multiplication generally actually will be for scalar multiplication. So if you use a tensor, let's say a 3x3 matrix, we'll get two different answers if you use the two different operators. And here, so we'll define our we'll define the model here. Instead of y, we are just using it as model, and that will be the same over here. What you have done, like x matrix multiplied with w transpose, then plus the bias. And now so it will make our predictions. So we have our 5 predictions, and each column is for apples and oranges, and we also have our gradient with respect to that we add. And now we can see our predictions and targets are like not they're not the same at all, because their weights were randomly initialized. So now we have to update our weights, and to do that we'll actually define a loss function or cost function, whatever. So that will be same as what we have discussed earlier. We'll be using mean squared error. So we just take the difference between the inputs, square them, and sum those inputs, and then average them. Uh, yeah. So you can see our loss is like around 49,000 something. So we have to minimize this loss. Like yeah, closer to zero will be much better. So to compute the gradient, we can just use loss dot backwards. You can see here our loss also has a gradient function. So we can calculate the gradients with respect to our weights and biases. Yeah, so we can see that we can calculate our weights, the gradient with respect to weights and biases, and we have this. So now we have to just update our weights and biases according to this gradient. Okay, now so we have yeah, we've already seen that we can use gradient descent to update our weights. So in general, what we do is, let's say we have a function like this. This is our loss and this is our weight. Yeah, and we have to achieve this local minimum, right? We have to minimize and we must minimize the loss. So let's say we are over here, for instance, and we calculate the gradient. So the gradient is positive, right? Because the angle is in anti-clockwise. The gradient is positive, so we must move left, right, in negative w direction to reach our local minimum. And if we are over here and then we calculate the gradient will be negative because the angle is in clockwise direction. But if the gradient is negative, you have to move in the positive direction. We have to move towards the right. So whatever the gradient is, you have to just move in the opposite direction with the same magnitude. So yeah, just remember that. And yeah, Pytorch actually doesn't make the gradient zero on its own. So after every time we update our weights, we have to make them zero so that we can calculate the gradients on the new weights instead of just adding them to the previous weights. So we have to just make the gradient zero, and now we can like update our weights. So the process will be the same. So after defining the model, we'll just take our predictions, we'll calculate the loss, and we'll calculate the gradient with respect to that loss, and then we'll update our weights. So here they've already explained about learning rate, right? We'll just multiply the learning rate with respect to the gradient and then subtract with the weights, and then we'll get our new weights which minimize the losses much further. uh, yeah, so now we'll see the weights are updated, and our loss is much less. It's now around 33,000 as opposed to what we got around 49,000. So now we know that because you have used learning rate as very small, the updates are very small. So we might have to run this loop. We might have to run the same algorithm like several times to get to converge on the loss. So like let's say we have run for like 100 times, and now our loss is around 253. Yeah. So if we run for much longer, loss keeps decreasing. So yeah, for running it for around 1000 epochs, our loss is around 26, and now our predictions and targets will be much closer to each other. Yeah, so this will be implementing linear regression in Pytorch, but actually you won't be like using this in general. You will be using the built-in Python libraries that we'll be discussing in the next tutorial when we'll be learning about neural networks. Okay, so anybody has any doubts? Yeah, we'll be sharing this notebook, so if you get any doubt, then also you might be able to ask us. Yeah, I guess Ujjwal had something to share regarding the assignment.
Sure. Sure, you can continue.
Yeah, am I audible?
Yes.
Yeah, hello everyone. As the duration of the workshop is reaching around 2 hours, so we it's quite evident you might all be exhausted by now. So I don't think it's the right time to initiate the assignment discussion. So we are postponing the discussion to a new date and we will inform it to you uh, soon. So till then, stay updated on the WhatsApp groups, and the links for those groups are there on the Teams itself, so you can join from there. Thank you.
Okay, so should I stop the recording, right?
Yes.
Yeah, you can.
Okay.